So in this problem we have an elastic collision between an alpha particle and a proton. So first here's a proton just sitting there, and the alpha particle comes in and collides with the proton. And we have conservation of momentum, so the momentum initial, which is just the mass of the alpha particle times the initial velocity of the alpha particle, equals the final momentum, which is just the momentum of the alpha particle after that collision, which is its mass times its velocity, plus the mass of the proton times the mass of the proton after that collision. Here we can cancel out the mass of the proton and we have this equation. Now we also have conservation of energy, or conservation of kinetic energy. So this equation was from conservation of momentum, but from conservation of kinetic energy we can write out another equation that describes the collision. Okay, so remember that conservation of kinetic energy also implies this relationship between the relative velocities. So we have that the difference in the velocities of the two particles before the collision equals the negative of the differences between their velocities. Okay, so from this equation we find out what the VI is just equal to the difference between the velocity of the proton and the velocity of the alpha particle after the collision. So we can plug that into the original equation that we had, and we get this. Okay, so now it's just easy to simplify this. So we have an equation that relates the velocity of the proton to the velocity of the alpha particle after the collision. And we can write that the velocity of the alpha particle after the collision is 3/8 of the velocity of the proton after the collision. Okay, so we have this equation that's going to be useful for us soon. So now we know also that after the collision the particles move into a region with magnetic field. So here's a proton, here's the alpha particle. After they collide, they both move into this region where there's a magnetic field pointing into the board. So here the motion of the proton in this magnetic field is described by, well, the magnetic force of the proton feels is given by this, and the charge is E, the velocity of the magnetic field, the sine of the angle is 90. So the force the proton feels, the magnetic force, is just E times the velocity times the magnetic field. And this force, which is given by this, equals the mass of the proton times the velocity squared divided by r, because it's going to have circular motion. So we have this important relationship. Okay? So now we can simplify to find the velocity of the proton after the collision. So we have it in terms of things that we already know the value of. So now that we have the velocity of the proton after the collision, we write down something that describes the alpha particle's motion. So the alpha particle's motion in the magnetic field, we have that it feels this force, this magnetic force. The charge of the alpha particle is twice the charge of the proton. And this simplifies to this. Now, the force that the alpha particle feels is just its mass times its velocity divided by the radius of the alpha particle, because it's, again, doing circular motion. So from this expression here, we could easily solve for the radius of the alpha particle. It experiences circular motion with this radius. So the velocity of the alpha particle, we already found before that it's equal to 3/8 of the velocity of the proton. And we also have an expression for the velocity of the proton. So now we can plug that into Vp in this equation. And so we have that that's equal to this. Here we plug in the velocity of the proton, which we found before. So now we find the radius of the alpha particle to be given by this.